So the critical path is the bit or data path in a circuit, in our case a multiplier, that has the worst propagation delay. And sometimes, or you might think that this would be the most significant bit, as that's the bit that acts last in the circuit, but that's not always the case. And it's important to know what the critical path is, because you can't clock your circuit any higher than that critical path. Otherwise, there'll be errors. And so for 2A, here's the math to find VM, which is generally V out equals V in. So you just take V out max minus V out min and divide it by 2. And then that's just 6 over 2, and you get 3 volts. And then for 2B, finding the gain, use this equation here. So you have G equals K prime over 2 times VM, which we just found, minus VT, which in this case is 0.5 volts, and then times 1 over 2 times the length modulation term times IDS. And so the gain is dependent on the current from the drain to source. So we need to find that current at VM. And so we use this equation here. And that comes out to 625 microamps. And then from there, we just plug that value of IDS into our equation, and we come out with a gain of 11.43. Alright, and then solving for VIL, you use this equation. So you know that V out max is equal to the negative gain times VIL plus VM times 1 plus the gain. And then plugging in the values we've found for the other things, we know that V out max is 6 volts. So we plug that in here, and then we come out with 2.74 volts. And then for 2D, we use a similar equation to 2C to find VIH. So we know that V out min is equal to the gain, the negative gain, times VIH plus VM times 1 plus the gain. So plugging in those values, we get this, and then we need to isolate VIH. And so we have VIH is equal to this quantity, and then we can simplify that to 3.26 volts. All right, and then so on 3A, when we try to solve for the value of WP, so the width for the PMOS, and we're trying to make the propagation delay from high to low equal to the propagation delay of low to high. And since these two values are dependent on the current that travels through the NMOS or the PMOS, so to make these values equal, we have to make the current that travels through the NMOS and the PMOS equal. So using the equation for IDS, this is for any sort of transistor. This equation we've used a bunch of times. We're trying to find this. So how can we get the drain to source current from P equal to drain to source current from N? And then we plug in these values, and so for the drain to source current for P, the unique terms we have are K prime of P and then W over L for P, and then the same thing for N. And then so we can cross out terms that are the same. So the VGS minus VT we can get rid of, and the 2 we can get rid of, and we end up with this. And then we can express that as a ratio of K prime over P, K prime of P over K prime of N. And then that is equal to the ratio of W over L of N over W over L of P. And then we can substitute in the values for K primes. We come out with this ratio. And then the values of W over L and and L. And then we can simplify that, and we find that WP is equal to 10 micrometers, which is the value of L for the PMOS, times the ratio of K prime of P over K prime of N, and that gives us a value of 14.74 micrometers for WP.